Hello everyone, my name is Zhao. In this presentation, I will introduce our work titled Effectively Scheduling Computational Graphs of Deep Neural Networks Toward Their Domain-Specific Accelerators. The presentation is composed of the following content. Let's start with the introduction. Existing DSAs have formed a common abstraction as shown below. It includes D clusters, each of which contains C cores and U compute units. The UCUs are often with an LB buffer, while the C cores are connected and with a GB buffer. This abstraction can be used to instantiate many DSA accelerators. As such, developing a scheduling approach for this abstraction is important. Unfortunately, existing approaches cannot fully exploit its computing power. We use the computation graph of ResNet 50 as an example. The first limitation of priori work is that they decompose this computation graph by grouping nodes without considering hardware architectures, which produces more small kernels and more off-core data movements. Second, grouping nodes this way also misses the optimization opportunities of a cross-layer instruction scheduling. Third, priori work did not consider the so-called imbalanced memory usage distribution across a network's architecture, thus underutilizing the LB buffer of the DSA abstraction. To address these challenges, we need to resolve the following problems. First, we need to construct coarser-grained subgraphs to generate larger kernels and convert off-core data movements into on-core data exchanges as much as possible. Second, we must be able to hide memory latency and better exploit the parallelism across the use of the DSA abstraction. Finally, we should make use of the imbalanced memory distribution to better utilize the LB buffer of the DSA abstraction. With such design rationale in mind, we design and implement our new scheduler, GraphTurb. The core idea of our scheduler is to maximally preserve the input tensor in LB to convert as many off-core data moments as possible into on-core data exchanges. So, for the sake of clarity, we reproduce the 4 stages of the ResNet 50 model and assume that each stage reduces the size of an image by 2. We also suppose that a cluster of the DSA abstraction processes 8 images. GraphTurb first constructs larger subgraphs by fully considering the underlying hardware constraints. For this example, GraphTurb builds a subgraph for each stage. Next, GraphTurb splits these subgraphs into 8, 4, 2, and 1 instance respectively. It first executes 2 instances of stage 1 subgraph at timestamp 1 and 2, and next executes 1 instance of stage 2's subgraph at timestamp 3, and so on, which forms a scheduling order as the members shown here. The instances of the same subgraph labeled with the same timestamp are executed in parallel. So in particular, suppose that the LB buffer is saturated when executing an instance of stage 1, because each stage is reduced by 2, a scheduler would underutilize the LB buffer if it executed 1 instance of stage 2, stage 3, or stage 4. However, GraphTurb executes 2, 4, and 8 instances of stage 2, stage 3, stage 4 in parallel, which means it makes full use of the LB buffer while exploiting the parallelism across the cores. Now we first introduce how coarser-grained subgraphs and their instances can be constructed and scheduled respectively. We use 5 steps to achieve this goal. The first step is collecting hardware information before constructing subgraphs. This step is implemented using algorithm 1, which collects the required hardware information into split infer. We collect hardware information to get graph term, when to stop node grouping. Split infer includes information including which loop dimensions of a tensor should be split, the splitting factors, and so on. We assume that each OP has only one output tensor, and the algorithm computes split infer for the single output tensor and propagates such information to each of its input tensors. We also define a formula to select the most appropriate dimension when there exists more than one splittable candidate. Once split infer is determined, GraphTurb tries to form larger subgraphs. The second step is to perform this task, which is implemented by algorithm 2. First, GraphTurb sorts a computational graph in a topological order. Next, it groups nodes to form larger subgraphs by considering 3 producer-consumer relations as shown below. With such a method, GraphTurb can obtain larger subgraphs and split them into multiple instances. After that, GraphTurb can try to determine a proper scheduling order of these subgraph instances. GraphTurb currently uses 2 heuristics to order such subgraph instances. The first one is a BFS heuristic, which obtains a scheduling order like this. The second one is a DFS heuristic, which is implemented by algorithm 3 as shown here, resulting in a scheduling order like the one shown at the bottom of this slide. This is the scheduling order used to explain the core idea. A more intelligent NLP-based heuristic is under construction and will be released soon. So the fourth step is to bend each of such ordered subgraph instances to the multiple cores of the DSA abstraction. Algorithm 4 shown here is used to achieve this goal. One may also notice that this algorithm can also infer at which buffer scopes the output tensor of a subgraph instance should be declared. Specifically, this algorithm visits the scheduling order of subgraph instances in a reverse order and next tries to infer both core banding and buffer scope declaration. The final step of scheduling subgraph instances is to concatenate the output of multiple subgraph instances. The figure below shows how the results of this step when applied to the 4 stages of ResNet 50. The figure on the right explains how to implement this functionality. A copy OP is inserted when the memory scopes are different from each other, while a redistribute OP is inserted when the bounding strategies are different. How GraphTurb is generalized to handle more complicated cases is discussed in the paper. So the next task of GraphTurb is to generate larger kernels. To achieve this, we expand a subgraph instance as below. Our kernel generator first performs loop fusion within a layer, i.e. the rightmost port, such that the operators within this layer can be fused. After the internal of a layer is fused, we do not put its output back to DDR, but still let it remain in the LB buffer with both compute and memory-intensive OPs considered. Also, we always release the space consumed by an output tensor once it is no longer used. In case the total size of these tensors exceeds the RB buffer's capacity, the one with the longest liveness across multiple computation tasks is spilled. On the right of the figure below, we can promote a weight tensor as early as possible, which is implemented by first copying its tensor from DDR to GB and next hoisting the tensor from GB to LB. The latency of these promotion statements can be hidden behind an earlier executed layer, and multiple CUs can execute computation tasks in parallel. The figure below shows how this optimization is performed, which implements the across-layer instruction scheduling. We finally report the experimental result. We conduct experiments on STCP-920, an SoC DSA platform which customized the DSA abstraction by instating its parameters as below. We experiment using the following models and compared performance with TVM, OSDI, and a crafted implementation. So in this presentation, we report the performance by selecting the optimal numbers of batches per cluster. The results of multiple clusters are also reported in the paper. This table summarizes the configurations of each model. TVM's throughput is listed in the rightmost column. We show the speed-ups of each approach over TVM's data in this figure. TVM fills OPs within a subgraph. OSDI does not benefit from the imbalanced memory usage distribution, and the wonder-crafted implementation is not scalable. So on average, GraphTurb outperforms all of the baseline approaches. Note that we also report the compilation overhead of different approaches used in this experiment. Users can refer to the paper for detailed results. Now we report the ablation study by considering 4 variants. The first variant implements the functionality of TVM, and the second variant outperforms the first one, which demonstrates that converting off-core data movement into on-core data exchanges indeed makes sense. The better performance of the third variant demonstrates the contribution of exploiting the imbalanced memory usage distribution. And the fourth variant demonstrates the effectiveness of the across-layer instruction scheduling method. We also conduct experiments to demonstrate how hardware is utilized by GraphTurb. The table below shows how GraphTurb makes use of fast local memory, and the figure below shows how GraphTurb utilizes the VME and MME of the target platform. Note that we also demonstrate the scalability of GraphTurb to GPU in the paper. The results show that GraphTurb can outperform Qtless implementation with and without convolution fusion by 1.06 times and 1.23 times respectively. Finally, let's summarize the contribution of this work. So first, we recognize the importance of considering hardware architecture at the graph partitioning level, which enables the synergy between network and hardware architectures. This synergy reduces off-core data movements, better saturates the available local memory, and empowers across-layer instruction scheduling. Third, we design and implement a novel scheduling approach called GraphTurb, addressing the deployment issue of DNNs on DSA chips and offering insight to other platforms. And finally, the experimental results demonstrate that GraphTurb can outperform 2 state-of-the-art tools and achieve performance comparable to the vendor-crafted code. So that's all for the presentation. Thank you for your listening and your interest in our work.